Hello. And thanks to all of you here and all of those of you who are online for coming to the SEFS weekly seminar. My name is Van Kane. I'm a research assistant professor here in the school. And I'd like to introduce my friend and colleague, Malcolm North. He and I met over a dozen years ago now in the best possible way over beer in a forest. And since then, we've had many times in forest. We've collaborated on at least half a dozen, if not more, papers in that time. And I'll read, some notes from his formal bio. He received both his master's and his PhD here under Jerry Franklin with his PhD. Oh, not the master's? Oh, master's was at Yale. His PhD was here with Jerry Franklin in 1993. He is currently a research forest ecologist with the U.S. Forest Service's Pacific Southwest Research Station. He also is an affiliate professor of forest ecology in the Department of Plant Sciences at the University of California, Davis, where he has mentored a number of students and postdocs who've gone on to be very prominent in this field. And today he's going to be talking about a critically important question, resilience in our dry Western forests. So with that, I'll let Malcolm take over.
Thank you, Van. If it's okay, I'm going to remove this since I'm up here. Thanks a lot for having me here today. I'm going to cover a lot in this talk, but hopefully you're going to see, at least where I'm trying to present, is two ideas that kind of dovetail into each other that, at least to my mind, are fairly important in terms of our ability to deal with this wildfire problem in the West and what we need to do in terms of thinking about both the nature of the treatments that we put out there, but also how to increase the pace and scale of those type of treatments, since at this point, frankly, we're getting our butts kicked all over the place in the West by these fires. So it's based on two papers. One of them's out in the Journal of Forestry on a concept called Pyrocyniculture, and the other one's under review, trying to take on this issue of resilience, which I reluctantly got into, since probably like all of you, when I hear the word resilience, I kind of end up rolling my eyes most of the time these days. But I'm going to see if I can try to address it here. So, oops, let me see. Let's just do it that way. Okay. Just a brief, recapping of the context of the situation that we're in. I think all of you know this very well, but just a couple kind of factoids. And excuse me for a little bit, I'm going to be talking mostly about California in this talk, because it's a lot of where I'm familiar with the data and the situation, but I think a lot of what I'm talking about is relevant to much of the Western US, and as well as Washington State on the east side of the Cascades. So hopefully this will be relevant beyond the scope of California. But just some quick numbers on things to kind of put this in context. Just within the last 16 months, 15% of California's 40 million acres is burned. In 1 year, we've had what we were estimated to be $150 billion in economic losses just in California. The last decade, 43,000 houses burned, 173 fatalities. And most of these forest fires, most of these forests that these fires are burning in are low to moderate severity fire regimes that are relatively healthy, if I can use that word, when you get frequent low severity fire in them, largely cleaning out the forest. But a lot of these current wildfires we have are a much different nature of high severity crown fires. For those of us that love big trees, kind of a depressing fact was the Castle Fire has killed 10% of the world's mature giant sequoias just in one burn. And of course, the other thing that's going on at the same time is that with fire suppression, we have a densification of the forest. And for all the ways we like to think about the glories of trees, one thing they are is just gigantic straws, which are stuck in the ground. And in essence, with all those extra straws in the ground, we had a pretty significant mortality event in 2012 to 16, in which resulted in about 150 million trees dying in the Sierra Nevadas. And one of the reasons why I'm bringing that up is that what came out of the other end of that drought was a tremendously high load of fuels in the southern parts of the Sierra from all these dead trees. And it produced some fire behavior, which we have never seen before, at least in my experience of what many of the people I know working on the fire were talking about. This pyrocumulus cloud in the lower right reached over 55,000 feet in height. And a friend of mine who's a fire nerd said he did a back of the envelope calculation that to be able to loft that much water vapor and carbon that high in the atmosphere, you're talking about an energy release on the size of a small atomic bomb. So we are seeing fire behavior out there, which is a product of what I'm going to call compounding disturbances. And the reason why I want to raise that is that I sometimes think when we're talking about resilience or trying to figure out what we're going to do with these forests, we often focus mostly, almost exclusively sometimes in the fire aspect. But this is where the future is going, is one disturbance event like this drought mortality feeding into and amplifying another disturbance event. And because of that, I think when we're thinking about resilience in these systems, we need to think about more than just the fire angle. And I'll go into that in a little bit more detail here. So the first part of this is operationalizing forest resilience. And as I said, if you're rolling your eyes, you're like me. I've kind of hated this word resilience for a long time, but it is now baked into much of the way that people are talking about forests. And in particular, for Forest Service lands, which is a lot of the western part of the United States, it's written pretty strongly into the forest plan revision, the 2012 document, which is driving the development of new forest plans on all the national forests. But resilience has been pretty difficult to define, and no shortage of reasons, but confusion over the types of resilience. Are we talking about engineering versus ecological versus civicultural resilience? What's the scale we should be applying it at? The tree, the ecosystem, the landscape. There's a bunch of sloppiness in the way it's been used in the literature. So you have kind of a confounding of resistance and response and resilience. And then as Paul Hesberg and some other folks have pointed out, you're going to have different levels of resilience and different way that systems respond depending on their endemic disturbance system, as well as the forest type or the community that you're talking about with disturbance. And there was a nice article written back in 2007 in which they said, the quote was, resilience, a malleable term that facilitates communication across disciplinary boundaries by creating shared vocabulary, bridging the gap between science and policy. And they were writing about that kind of in a praiseworthy way, but what they're also saying by saying a malleable term is basically it's damn hard to constrain it and create a scientific measure out of it that you can apply to forests or to other ecosystems. And that, I think, has always been the bedevilment with resilience. So in any case, I'm going to argue that at least defining and operationalizing resilience becomes much more tractable when we put it in a specific ecological context. So then we can start creating some bounds on it. So for the rest of this talk, I'm going to be talking about dry, frequent fire forests in particular. So one of the ways that I first started approaching this problem was to look at the ecological concept literature, the theory literature about what does fire actually do in these systems, so that we can kind of understand it in a conceptual way that might be able to build a little bit of a better definition for it. And you know, one of the common themes out there is that fire is similar to herbivory, where consumers control the ecosystem biomass and the species composition. You know, if you think about grazers on the African savanna, if you eliminate all the predators like the lions, you're going to have a pretty large expansion of the herbivores, and they end up controlling the relative amount of biomass that's out there in the systems. So when predators are scarce, you have little plant competition because herbivores are the top-down control on what's actually growing out there, limiting plant growth more than resources. Since fire is considered analogous to that kind of system, if you think about flipping that analogy over to fire systems, if you're talking about an absence of suppression, like the elimination of predators, fire is frequent. It's what's limiting tree density more than resource availability, water, light, so on, and significantly reducing the levels of competition. So to somebody foreseeing this, they would consider this forest understocked or wide open. And one of the things I found interesting is we have a bunch of surveys in the Sierra Nevadas done at the turn of the century, and one of these was by Lieberg. And this is a quote from one of his surveys in there. "The suppression of young growth has always been one of the serious results of fires. The land does not carry more than 35% of the quantity of timber it is capable of supporting." Now, besides the timber focus there, it's probably a pretty accurate representation of the fact that the fire is basically suppressing the amount of total biomass that you could pack into that system. But if you think about that, if a system's evolved with that for eons, it's likely to also have a stability more built into it in an environment that has very little competition. That's what I'm going to argue here. The lower right is a classic diagram done by Jerry Franklin talking about tree mortality. It's called some people call it just the death spiral for trees, but it basically has this concept that once you start to weaken a tree, unless it can break out of the stresses that are limiting its growth patterns, it can eventually spiral down into mortality. And certainly one of the things that we know pretty well from a lot of tree studies is that relative growth rates in trees are a pretty good predictor of whether a tree can respond and rebound from a stress into its system, or whether it continues down this spiral that eventually can lead to mortality. So if we're going back to that herbivore predator type of relationship, thinking about it in forests, the flip side of that is that in fire's absence, which is the condition we mostly have in much of the Western United States, live tree density and biomass is going to accumulate, leading to really increased competition for growth resources and reduced tree vigor. And again, if you think about most of the exposure, the way these forests developed was in a relatively low density type of condition. This is a different type of stress than the stress you would get from a fire burning through, or a 1 or 2 year drought, or an exposure to pests. It's fundamentally different because it's internal to the system, but it's also, rather than a pulse, like an event that happens 1 or 2 years, it's a continuous press. There's a lot of ecological literature that suggests there's fundamentally very strong differences in the way that organisms, particularly plants, respond to pulses versus presses. And I'm going to suggest that that's probably one of the things that is making these systems so unstable. Is most of the Western forests have gotten through extreme droughts. They've been through wildfires before, even if they weren't as severe wildfires. But we're seeing trees now sometimes die with very little minimal stress exposure. Like even after a restoration treatment is done and the density is reduced, you still lose trees sometimes to very low intensity prescribed burns or the cutting of the neighboring trees. And it's suggesting that something is predisposing the trees already to a condition in which their vigor is so reduced that something that's a fairly minor stress can actually lead to the mortality of the large overstory trees that may have survived 400 or 500 years of pulses of stresses, but not presses, continuous exposure. If I'm going to talk about resistance and resilience, I'm legally obliged to put a cup and ball schematic in there. So that's what it's doing up there in the right. Those kind of schematics drive me nuts. But what I want to do is just kind of quickly define these terms so we can continue moving forward on thinking about what this means for operationalizing resilience. So I'm going to suggest that resistance is a measure of persistence when exposed to a stress. And it's focused on minimizing change. So resistance treatments are often, not exclusively, but often designed for specific stresses. And my point here is that a lot of what we're doing in forests is fuels reduction. It's geared at one particular stress, fire. But that's not resilience. Resilience is a broader community level response of how a forest deals with stresses. And it's fundamentally trying to retain its essential structure and composition in the face of these stresses that is beyond a single particular stress like fire. A resilient ecosystem has to be resilient to fire, to drought, to bark beetles, to a whole host of potential things which might change its composition. So resilience is a much broader type of ability to resist this kind of change. And the reason why I point this out again is to go back to that early example in the creek fire. We're in a world which has many stresses now beyond simply wildfire. And so to make a forest particularly resilient to this, it has to be resilient to these stresses that look like they're going to continue to compound each other and really reduce forest's ability to be resilient to what's happening to it. So I'm going to suggest that the hypothesis here is that resilience treatments need to restore tree vigor, which we often measure by looking at increment growth, by creating low densities characterized by little resource competition, and that may have been a fundamentally defining character of frequent fire forests. And I'm going to go one step further and suggest that if we're going to make this useful, we have to develop a measure of it that is something that civiculturalists, who are often the boots on the ground doing this stuff, are familiar with using. And in this case, I think we're in pretty good luck, because something commonly used is actually a fairly good indirect measure of competition within these stands, which is relative stand density index. Probably, as all of you know, stand density index is a combined measurement of size of trees, the biomass of the trees combined with the density of the trees. And the relative measure of that is what is the level of stand density index you have against the maximum level that that particular forest type could carry. So I'll give you an example of this in a minute. But what I wanted to do was take some historical data sets that we have and test this idea. If we look at these pretty extensive inventories that were developed around the turn of the century, what do they tell us about what the forest looked like? And fortunately, again, we have in California some of these that are archived. If you dive back into the federal archives, you can find these things. But I'm just going to highlight inventory that we used in this paper, both on the Stanislaus and Sequoia, that were pretty extensive, basically 5 to 10% samples of the entire area that they were done over 644 plots covering more than 10,000 hectares. And you can see the patterns here in purple and green for these two different areas. And the circle indicates where the photo below it was taken, approximately somewhere in that area. And it's a good indication of kind of what's happening here between historical forest conditions and where the modern forest is developing out is. You can see this cluster of big pines here in the center, which is kind of the backbone of what the forest used to look like. But all of this ingrowth has come in, much of it white fir, that has come in with fire suppression. And this forest is kind of right in that transition of going from a fairly low density open system to something that has much different density and diameter distribution than what the historical forests look like. So we took these areas with the plots and looked at the modern current conditions, well, 2011 conditions, using a recently developed data set called F3 which for various reasons I think is a little bit of an improvement over the GNN data set, which is otherwise commonly used for assessing forest conditions that are out there. So what did this forest look like? So you can see between these two photos what an area called the Bear Creek Ranger Station, and I will confess that unfortunately that photo is not within the limits of this thing, but I think it's within the limits of where this inventory was done. But I think it's a pretty good representation of the changes that are going on in these forest conditions between these two different time periods. Over here, the top row is the 1911 condition, and the bottom row is the 2011 condition. Notice the difference in the scale of the y-axis, literally a tenfold difference in terms of the scale. And you can see that the conditions we're talking about in these three different forest types that were within this area sample, the pine mixed conifer, the drier xeric mixed conifer, the mesic mixed conifer. You're looking at about 47 stems per hectare of an average size ranging between about 66 and 75 centimeters. Few but very large trees dominating the system. No particular surprise to any of us who've worked on these kind of data sets before. The current condition, 347, 422 stems per hectare. You can see the way the densities increase by 5 to 6 fold in there, and with a corresponding drop in the diameter conditions. Again, pretty familiar to us, but think about what it means in terms of the way these forests evolved versus the condition, the stresses that they're put under the modern system. This to me is the one that's kind of interesting. If you're familiar with stand density index, you have a calculation for a particular plot or an area, and you look at the percentage that that value makes up of the maximum for that particular type. So just for this pine mixed conifer, I believe the maximum is 550. It's done by taking a whole bunch of calculations of stand diameters out there and then putting it on a log scale, and you can make an estimate as to what that maximum is. But these are the absolute values, both in metric and English, for these. 206 compared to a modern condition that's about 2.5 times that. Same kind of thing going on here in the xeric mixed conifer. I'm going to switch from these absolute values to putting them in relative stand density index, because this gives you a sense of what the competitive environment is like in these stands. So look at these values here. We're talking about 23% at the maximum here, 25, 28% in the historical forest versus levels that are more in the 45 to 60% range. And in silviculture, the way this is broken out is that if you have relative densities below 25%, it's considered free of competition. 25 to 35, partial competition, full competition at 35 to 60, and IM or imminent mortality once you're above 60%. Look at the distribution of these. The 1911 stands, almost all of it is down here in the free or partial competition phase, as the modern conditions almost all appear in the full or imminent mortality. And these violin plots show that distribution for all of these plots that we were looking at. And you can see the way the distribution of those violins basically gets inverted. It flips so that most of modern conditions are up here in this level considered full competition to imminent mortality. I would be the first to acknowledge this is not a mechanistic study. We're simply looking at correlation of a theory that I'm proposing about resilience in these systems being inherently dependent on low levels of competition. But this data certainly supports that, at least in historical forests, you had densities so low that you probably rarely had competition in these systems. Whether that's what's making the current system so lacking in resilience, I can't say for sure. But to me, it's a very compelling argument that at least those conditions historically were fundamentally different in terms of their competitive exposure from what we have in modern conditions. You might say, okay, well, you know, what's the big deal? We know that historical forests had low densities in the past and little competition. So what? We've known for a long time that trees have better vigor when they're grown with little competition. Their growth rates are better. They respond better to stresses involved in them. So what's the big deal about saying, well, we had low densities in the past and we don't anymore? The reason why I'm going to suggest this is really fundamentally important is, to me, it's like the guy behind the curtain in The Wizard of Oz who's actually pulling all the levers and he's just out of sight. If you're familiar with forest management techniques, particularly the models that drive the way you plan forest development, FBS is the main one the Forest Service uses. Variations of it are used by private industry. It's all predicated on stands developing under competitive pressure. And competition is what drives stand dynamics in these systems. I won't go through the explanation of all the stand density management diagrams, but this is how silviculturalists figure out how many trees to plant, how they're going to grow, whether you're going to thin or not thin, and what kind of diameter you're going to get in the end. And that's the way stands are grown and managed in much of the Forest Service, and particularly on private lands. It is the dominant method. Looking at this. And I'm suggesting here that if you really wanted to make these forests resilient, you'd produce an environment with almost none of the competition, which is what fundamentally drives the development and the management of most stands. A typical way that forestry practices look at this is maintaining a stocking level above 35% of SDI, which is where you're getting competition. And then you keep on knocking it back and thinning it when it approaches the zone of imminent mortality at 60%. So you're kind of bouncing the stand back and forth in here, getting bigger trees, but reducing their density, always keeping them competing with each other to move the stand structure towards your desired stand. So if we said that really to make resilient forests, we want a forest with very little competition, it's pretty heretical compared to the way most stands are modeled. And I was interested to see, well, you know, what would it mean in terms of the level of treatments that you'd have to do out in the landscape? So we looked at those areas where I was showing you the 644 plots and said, what in terms of the current definition of the Forest Service, how much of those would you have to fit? And the Forest Service prioritizes areas for fuels reduction, density reduction, when you reach a relative SDI at 60%. We did that with those 644 plots. We'd be treating 48, 25, and 0%, depending on the forest type, pine, xeric, conifer, of those plots, to be able to keep them out of imminent mortality. But if we looked at producing a resilient, possibly a resilient forest, I'm going to suggest, by minimizing competition, you'd have to treat 91 to 100% of those plots. If this is a valid argument, it means that we are grossly under-treating the amount of forest out there that needs to be treated to make it resilient. And furthermore, we're not even getting it anywhere near to the low open density type of conditions that might be fundamental to resilience. Furthermore, to my mind, it opens up the possibility that what you could do with this system is try to create heterogeneity out there, trying to use the SDI values, but using the range of those values, which is in the table here below the values, to vary the relative density that you've got out there, where you've got higher percentages of SDI in wetter spots, places that can support more of that because water is the limiting resource most of the time in these systems. And you'd actually have lower SDIs in pretty dry spots like the southwest slopes that are steeper and don't hold water as well. Gives you the ability to create variability on the landscape where you're trying to bring the forest structure in sync with the resource availability, the key resource being water in this case. I do want to emphasize, though, that trying to keep competition at a minimum does not mean regularly spacing trees the way we often replant them. Derek's here, who's one of the initial authors of this very important paper, realizing that the tree spatial pattern makes a real difference in terms of being able to create a resilient and resistant forest structure. This is an example of it in Yosemite, where you see this scattering of individual trees, the openings and the clumps of trees, which is really pretty fundamental to the forest being able to withstand fire. So I'm going to suggest that the important thing here is not only creating an open, relatively competition-free environment, but also getting the spatial structure right if we really want to create resilience. So that's the end of my resilience part of this talk. I'm going to now switch to this other part on pyrocyniculture, because if we're going to treat the forest and try to get it into a more resilient situation, doing it correctly at the stand level is very important, but it doesn't get us very far if we don't treat a substantial part of the landscape, because any individual stand is going to get overrun by these stresses if it's embedded in a matrix of untreated forest that really has very high levels of competition, reducing the tree's ability to absorb these stresses. So this pyrocyniculture approach was designed to say, okay, let's not wish for endless amounts of congressional money that's never going to come, or a real change in the way that we think about these systems. Let's try to diagnose the problem, figure out what's impacting most of the landscape, the limits of how you can scale this in current management practices, and what needs to change and how you pay for it. So that's kind of what this paper is fundamentally about. And I always start, when I think about these things, about what is really inevitable in these systems. And of course, what is inevitable, we know is going to happen, is it's going to burn at some point. And so you have two different fires you can choose: the current system, which is the suppression approach, which leads to these really high intensity fires, or we can become the agents of more of the fire that's out there on the landscape. And so the fundamental kind of credo of pyrocyniculture is you're trying to directly increase fire use in these systems, because this is preferable to this. And the only way we're going to get there is be more of the agents of that change, in which we're in control of the fire situation. And so everything I'm going to be talking about after this is trying to figure out a way to increase the amount of fire we can put into the landscape. So the first step in this is diagnosing the problem. Scott Stevens was the first one I know of to do this. I did it later in a 2012 paper, but we decided we wanted to update these estimates. And so what we're looking at here is 13 million Forest Service acres spread across the Sierra Nevadas. You figure out how many of those acres used to burn each year from the pre-European fire regime, to give you a sense, not a strict sense that you absolutely have to do that, but what's the ballpark number of fuels reduced acres that you would have had historically to maintain these type of forest systems. And going through this by forest type, you end up with 620,000 acres for a 13 million acre area. Sorry, these are in English units, but we were trying to reach a management audience, but there's the hectare value down there at the bottom to give you a sense. So this is saying roughly, if we were keeping up with this problem for the Sierra Nevadas Forest Service lands, we need to be treating about 620,000 acres per year. So then the next step was to figure out, okay, how are we doing currently? Are we even close to that? And this was a very painful dive into what the Forest Service uses as its database, a thing called FACS, which is really a nightmare to work with. But with a lot of persistence, we were able to calculate what the average number of acres treated over the last decade were. And there are two estimates here, because we wanted to be transparent about this. Often when you fuels treat an area, you'll thin it first, and then the next year after the fuels have dried, go and put fire in it. If you count those as two separate types of fuel treatments, you end up with this 93,000 acres. But in terms of progressing across the landscape, the two things are actually kind of double counting because they're in the same piece of land. So if you're looking at the unique footprint, you have about 63,000 acres. If you're looking at just whatever fuels treatments, wherever it was total, you're looking at 93,000. This is what the Forest Service usually puts out with their thing. But if you're looking at how far you're getting across the landscape, this is an important number as well. So what's the level of treatment? Well, at 63,000 acres, you compare it to that 620,000 acre value, you're doing about 10% of what you should be doing. So you're off by an order of magnitude. If you look at the total accomplishment area, where you're including the overlapping, you're looking at about 15%. So 1/10 to 1/7 of what we should be doing out there. These numbers were kind of depressing for me. It turns out that if you're going to thin a site, the average size of that is 36 acres. The average burn size is about 40 acres. And the average managed wildfire size is about 2,900 acres. So then the final piece of information to gather to put this in perspective is how much is wildfire burning across this landscape? The values vary hugely year to year. So I wouldn't put a huge amount of faith in the average, but it still gives you a sense of about 227,000 acres burn within this area. And I want to point out that 66 and 45,000 of those are actually burning at low to moderate severity. So wildfire is burning about 2.5 to 3.5 times the amount of area that the treatments are fuels treating within this landscape. So to my mind, the first thing that this says for a take-home message is if wildfire is having the biggest impact out there on the landscape, how can we leverage or use that wildfire? If we're thinking about the fact that half of that wildfire acreage is actually a favorable improvement on forest conditions, we could call it a treatment, an unintentional treatment, but a treatment that's moving the forest in the right way. And I'm going to suggest that this is where we get ourselves into a lot of problems, is that currently most of our management after these fires is focused on possibly salvaging the site or planting the high severity areas. But it largely ignores these low to moderate areas out there. And yet the fire's gotten us possibly halfway towards restoring these forests. So my suggestion is to use that natural treatment that's going on out there, and after wildfire treatment, harden the stand that remains there by doing the thinning to remove any ladder fuels that continue to be in there, and follow that up with prescribed fire after many of the snags have fallen down to reduce the fuels problem 7 or 20 years later. And you've leveraged the low and moderate severity areas in the wildfires to get you a 250 to 300, over 300% increase in the amount of treatments that you've got going on. The second concept has to do with this idea of managed wildfire. I'm just going to quickly show this slide because it sets up the following one. But in an old paper we looked at, I was getting tired of hearing people saying, oh God, if we just got serious about thinning, we could, log our way out of this situation, we'd be fine. I'm like, yeah, I guess I can investigate that. So we looked at each one of the national forests in the Sierra Nevadas going from north to south, the Movaca Pass and stuff like that, with the Sequoia and Inyo. And the height of these bars is the total acreage. And then we said, okay, how much of that could you actually thin on? So you take out the stuff that's not timber, you take out the wilderness and the roadless areas, you take out the land that's too steep or too far from roads to work on, take out the spotted owl, the riparian areas, administrative limitations. And the green is what you're left with in each one of those forests. Overall average of 28%. So there was another analysis we did looking at the spatial distribution of these, and basically showed there's no way in hell you can thin your way out of this problem alone. But there's just too many constraints on most of the places you're dealing with. And furthermore, for those who've worked with the National Forest on these type of projects, you know that thinning really can't scale to working at a pretty large extent. There's just a lot of planning hoops, relatively small project sizes, about 2,000 to 2,500 acres, sensitive species and archaeological constraints and all sorts of other things, and very expensive. But what that analysis does do is it helps you define areas that you could designate for managed wildfire. And so this shows for the Sierra National Forest, and the forest being the gray area and the green area. After you take away all the areas that are mechanically constrained, you're left with the green area that you actually can mechanically thin and do treatments in. And the Forest Service used this analysis that we did to say, we're going to identify the managed wildfire zones, which are the yellow and the blue, and base a lot of that on the areas that we can't get into. I think that fundamentally, when you're looking at managed wildfires producing about 3,000 acres of a shot for treatment, that it's substantially more efficient than trying to thin your way to success or burn your way to success with prescribed fire in each of these areas, when you can take a big chunk of a landscape and put it into a natural ignition type of parameter like the national parks do. Many of the national parks do. The third one is a bit of a two-piece thing here, but what struck me a lot about that analysis was the current way we're treating areas is incredibly small, 40 acres, 36 to 40 acres, and they're very dispersed. They're often not really connected. So you barely build up the inertial mass to really influence what's going to happen with wildfire here. So we had a bunch of discussions with people saying, how would you fundamentally change this? And one consensus was to use the WFDS, or the Wildland Fire Decision Support approach, which is always to take a landscape and build a kind of box around it so that you have control of fires that occur within it, because you have reduced fuel zones, either the WUI or these anchor treatments I'm going to show you in a minute, which kind of establish a perimeter around the area. And then you have various types of thinning treatments, which I'm going to show in a minute, but it allows you to try to get prescribed or managed wildfire to connect between these to build a larger mass that you've been able to treat in the landscape. And this is just a short schematic of what these three thinning treatments that I proposed are about, kind of focused on establishing this perimeter, or what I would call an anchor, that you can expand fire into this area from this anchor around the outside. Areas that you're worried about, ecological assets such as spotted owl nests, riparian areas, where you're going to want to make sure that you first do some kind of thinning to influence the way fire is going to burn through here, so that you can hold on to the asset that's important to you. And finally, heresy to some people, but you have to figure out some way to pay for it. And there are a lot of places where you have pretty substantial sized trees of saw log commercial revenue value that have grown in there with fire suppression, mostly the fir and the cedar, which can help offset the costs for doing much of this. A lot of people would say, well, these really aren't any different than thinning treatments that we have already. But I'd say the one fundamental difference is rather than talking or creating systems that suppress or contain fire, you're focused on expanding fire into the landscape. They're all based on trying to build off of getting more fire into the landscape. The other thing that has to go with this is relaxing the standards that we apply fire to a landscape. I often run into people fire managers who have been told from the supervisor's office or whatever, you know, you do the burn, but just don't burn up more than 15% of the overstory. And, you know, when you're on these fires, you don't have that level of control. It's a nice thought, but basically to make sure that you don't get 15% over mortality, the fires that are produced are often pretty low intensity. Fire is a pretty blunt tool, and I think we really need to change the way we think about it so we don't judge it against what you would have been able to achieve with a thinning operation, which is pretty surgical. But we have much more general type of objectives for it: density reduction, trying to produce this pattern, tree spatial pattern that's important, and trying to make sure that you're selecting more for the fire tolerant species. And something which I think people sometimes don't think about is there's a lot of variation within a species in relative bark thickness and branch abscission. And by putting the fire or the selective process back into the system, you're going to start favoring phenotypes, individuals that have thicker bark, earlier branch abscission, that can tolerate more heat. And so putting that selective pressure back into the system should be one of the objectives for us when we use fire. One of the other things that's obviously going on is if you're going to relax the standards by which you judge fire, you have this problem in that there's several particular values that we sometimes treasure and we spend a lot of effort trying to maintain. And I'm just going to pick one here because it's been the most impactful in California, which is spotted owls. And I'd say the interesting thing, just to sum up all these little notes, is that the owl biologists I've worked with in California have really come around to the fact that you need to be able to start pulling back from the fine filter approach of focusing on a single species to try to get the fundamentally shaping process of the ecosystem fire back in there. Because it was a wake-up call when the King Fire, which occurred in the Sierra foothills, wiped out about 2/3 of an owl demographic study that had been going on for 25 years. And the people running that study saw the owl populations crash 3 times harder than they ever had before from this one fire event. And all the people involved in that study are now very supportive of trying to get more fire back onto the landscape and stop trying to micromanage its effect on spotted owl habitat as the only thing that they're worried about. So one thing you have to say is, great idea, but you know, come on. You live in a state with 40 million people. You just can't use fire that much. Let's get practical. It's not really going to happen. There are air resource board restrictions, liability problems, all this kind of stuff. But the thing I always try to remember is that the United States actually puts 8 million acres of prescribed fire out there every year. It's just that 7 million of it is here. And the Southeast has managed to hold on to this culture of keeping fire into these systems, which to me is an encouraging sign that we somehow can build the cultural acceptance for fire. They do have a lot of key advantages, flat topography, wet summer weather, and so forth, that make it a little bit easier. But I would suggest there are examples out there that show it can be done. You know, the national parks have been pretty successful at doing it in California and southwestern Australia around the Perth area. They've managed to start putting fire pretty aggressively on the landscape to the tune of over 300,000 acres a year. And the managers who came up at the invitation of Scott Stevens that we talked to said, the surprising thing about it was really difficult at first. And then you started getting to a tipping point when you treated about 25% of the landscape, because you had a whole bunch of these anchors out in the landscape, areas that you put prescribed fire into, and you could build the fire off of those out between the connecting landscape. So it gives me some hope that what we think is impossible might be achievable if we can start changing the way that we think about fire in these systems. Finally, I think the pyrocyniculture has some benefits in the sense that mechanical thinning is always going to be too limited in scale, long NEPA process to get through. As prescribed fire has many limitations currently, but one of the things that's at least happening in California is that some of the national forests are developing programmatic NEPAs for putting fire throughout the forest that you just do once. And you don't have to build a project every time. If you get this approved, you can burn anywhere in the national forest without writing an individual EIS for each particular event. And the hope is, at least on the Sierra and the Inyo, that are some of the first to do these, talking about putting 50 to 80,000 acres of fire out there each year. I'd also suggest that fire reintroduces a key process. And because of that, you're probably building a little bit better adaptability to the unknowns of the future into the system by reintroducing the key process that really influences these systems. And if you ever start looking at maintenance, because you can't just treat a system once and then walk away from it, you're kind of locked into treating it every 15 to 25 years. Fire is going to be the only way we're going to be able to keep up with the maintenance of these systems. But there are some changes that need to be made. Many people have pointed out we need a Western prescribed fire training center that makes a very strong distinction between suppression crews and ecologically beneficial fire crews, and the two should not be able, particularly the fire suppression crews, should not be able to draw on those people who are trained for prescribed fire, because that's what's happened in the past. And we never ended up using those crews to really put prescribed fire out there. You'll need longer duration burn air permits because you really, if you're going to start working with fire at a big scale, it's going to take multiple days to be able to burn these things. And I'm kind of a fan of a process that Yosemite uses that I call kind of the push-pull process, which is rather than trying to do the fire in 1 day and 24 hours, you keep it going. And when the weather and adverse smoke conditions are coming at you, you herd the fire or push it into a low fuel area, like a granite outcrop or a previously burned area, hold it in there until the weather improves, the smoke dispersal improves, and then you don't put it out. It's still burning in there, but under favorable conditions, you pull it out of that area and you pull it across the landscape. And you get a lot of burning done that way because the ignition's already going. That's it. Thank you. Any questions from the peanut gallery here? See online. Okay.
How do you define managed wildfire?
Oh, God. Well, Derek and I were just talking about this, so it's a bit of a loaded question, but one of the things that we found by trying to just dive into and define the numbers of managed wildfires that are actually out there is that some of the more progressive fire managers, when they're on a fire, which they were delegated to as a suppression force, if they get good weather and the smoke is liable to go away from populated centers, you know, the dirty truth is they'll pull back and they'll let the fire burn and treat some of the acreage. And so for that day, they'll actually code it in this fact system as managed wildfire because it was being resource objective. But then if the wind picks up and the next day they want to contain it, the next day will be classified with a different number in the system and it'll be called a suppression fire. So I hadn't realized this. I thought you kind of just designated a wildfire as all suppression or all managed wildfire. But it turns out, at least the progressive people I see out there, they flip it back and forth depending on what the conditions are like. And to me, that's, you know, an appropriate opportunistic way of trying to get the fire to do some of the work for you in the landscape.
We have some questions online. What if we stop sharing this so people
Okay. Sure.
Somebody asked a question, so people online can serve it.
Okay.
The question online, I'll just read it for you. If one were to implement your suggestions for managing a forest for resilience, what would be the effect on biomass per hectare? All your measurements are about density of trees, but how does the biomass with fewer big trees and 11 compared to biomass with more smaller trees? That's partly because climate warriors are going to bring up the role of forest biomass.
Yeah, it's a great question. And I should clarify, I kept on mentioning density because it's often the way that stand density index is talked about. But SDI is actually a combination of density and biomass because you're taking in the size of the trees into the component. And to my mind, one of the advantages of actually managing for low competitive levels is what you're doing is you're taking the carbon out of what I would call the junk bonds in the system. You're cutting and removing the small trees, which are very susceptible to drought and wildfire, opening up the growing space, and you're channeling the carbon that's going into the system into the big trees, which is much more stable. It's like gold or bonds. That's where you want your growth to be in rather than the junk bonds. And so proper type of treatment, even though it's very low density, it is cultivating the development of large trees, and it stabilizes the carbon stocks much more than having it infill with these small things. It was because of the length of the talk, I couldn't go into this, but it's something that I talk about in the paper is that there's a concept both in carbon development and in what's called structural overshoot, if you're looking at drought response, in which you want to be very careful about not getting greedy and trying to pack too much carbon into the system or too much leaf area onto the trees, because when things get stressful or the fire comes through, you lose everything. You do much better by lowering your risk and directing the carbon into the stable resources in the system, which are the big trees. Okay. Let's see.
Is fire treatment feasible at stream side stands? Who may be researching fire treatment?
Yeah, another good one. We actually looked at this and put out a couple papers on it in at least California. There are some others that have been done in Eastern Oregon, I think, and in Colorado, which have shown that at least in these fire-dominated landscapes, much of the riparian area on smaller streams burned at about the same frequency and intensity as the adjoining upland fire. When you get to larger size streams, it creates enough of a microclimate effect and a change in fuels that they do have slightly, well, sometimes much longer fire return intervals and a different fire regime. But the thing that at least they've started appreciating in the Sierras is if you don't deal with the riparian areas, you leave a wick in the landscape. And where is that wildfire going to go? It's going to rip right up that wick, the riparian area, which has happened several times in California. The Angora fire I watched just went right up the riparian area and just toasted it. So although people understandably are very nervous about working in riparian areas, you don't want to be running skidders around in them or heavy equipment, but you do want to still be able to reduce the fuels in the thing, because you could treat the rest of the landscape, but you have one very flammable wick left in it if you ignore or walk away from the riparian areas. So I think you have to deal with that problem. Want to go ahead, Brian? I can't quite understand you, sir. Yeah.
One of the things I'm curious about is that California, especially getting good fire managed fire. I'm curious about your thoughts on how much, like, where the sort of seen the social license for that, especially given smoke, if that has changed in ways to the past fire. See if we can both directions.
So if I can repeat the question and just dive in if I'm misstating you, but it's from what I got, you have raised a good question about what is the social license in the general public for being able to put more fire out there intentionally on the landscape, because there's clearly been many issues about smoke. The Bay Area has been really upset for the last few years by getting inundated, and much of the Central Valley has as well. This is a hard battle to fight. The thing, at least that I emphasize, and many of the other people I've seen talk about fire emphasize, is starting with that point that you're going to get the fire one way or another. You're going to get the smoke. So wouldn't it be better to have most of that smoke happen when we're putting it out there under conditions it's going to disperse away from people and away from populations? But the dirty, well, actually not very dirty, it's pretty transparent fact is if you really are going to start putting a lot of treatment out there in the landscape, you're going to be burning a lot, and you're going to put a lot of smoke into the air. And frankly, it's going to be different than the kind of smoke that a lot of people are objecting to, because you can tell them it's going to come. You can try to get most of it away from the urban centers, but you still can't get around the fact California and much of the West is going to be a much smokier place than people have been used to. So right now we pretend that those wildfires are kind of acts of God, and sorry, you just got to put up with the smoke because there's nothing we could have done about it. Well, that's not at all the truth. If you were proactive, you would have been putting fire out in that landscape and getting those fuels reduced. But it is a tough sell, and I won't ignore that at all. The thing we have to try to communicate is that you're going to get the fire one way or another. And we can warn you when it's going to come. We can get most of that smoke to go into Nevada, where we don't care about Nevada. So you have Idaho here, so you say, but you know, there's no way around that fact. Yeah, you're talking about a lot more smoke. Yep. And I'm not sure the public is totally on board with that yet. So, yeah, Liz?
Expect that the stand and index might change with the warmer and drier conditions,
Yeah.
such that what we expect
Yeah, I mean, I'm spitballing, but since you're talking about competition as being one of the things which is the defining element of this, if soil moisture availability drops, which we would expect it to under climate change, then competition becomes potentially still happening even at these low levels, unless you drop it back even further. And so to my mind, if you're going to produce an environment that's relatively free of resource competition, as those resources naturally become more scarce because of climate change, you're going to have to lower those SDI values even further. And that's why I think, you know, when I've seen people look at pictures of what these forests used to look like, they went, oh my God, I don't want my forest to look like that. You know, there's only like 5 trees I can see, and I can see right into my neighbor's kitchen because there's no screening left or anything like that. We got a long ways to go, because frankly, even to get down to these levels of almost no competition is a hugely open forest condition. And if you then say, well, then we want to build it for what climate's going to be like over the next 50 years, it's going to be even more open than that. So unfortunately, that I don't know how we're going to deal with that problem, but it doesn't change the fact that, at least to my mind, this is something we're thinking about, this lack of competition. So.
We're going to kind of over time, and thank you for a really exciting talk. Get close to the microphone here, folks, so people can hear me say thank you. Thanks all online, and thanks for you in person. Thanks, Malcolm.
Okay, thank you very much. Appreciate it.